Hello, students. I hope you are doing well. Welcome again to Chapter 11 Refraction of Light. In the last lectures, we had defined refraction of light and stated the two laws of refraction of light. Today, in the last lecture, lecture 3, we are going to specify the conditions of total internal reflection and interpret the phenomenon of dispersion. Let's get started. Students, as I recall, the critical angle or limiting angle is the maximum angle of the angle of incidence at which the refracted ray grazes the surface of separation. That means that the angle of refraction is 90 degrees. So the incident angle that causes the refracted ray to skim right along the boundary of a substance is known as the critical angle or limiting angle. If the angle of incidence exceeds the critical angle, the ray is completely reflected and does not enter the new medium. This phenomenon is called total internal reflection. So, from Snell's law, we can get the formula of the critical angle IL or lambda or theta C, which is sine minus 1 of the ratio NR over NI. Note that always NR is less than NI. As a solved application, suppose light ray is traveling in a heavy flint glass of index of refraction 1.65 and once it strikes the boundary enters air. Calculate the critical angle of flint glass using Snell's law, knowing that sine theta 2 is 1. We get sine theta c equals n2 over n1. We get theta c equals 37.3 degrees. What does this angle mean? This angle is the limiting angle of incidence, beyond which the ray will not cross into air. That's what we are going to discuss in the next slides. Total internal reflection. What is this phenomenon? Total internal reflection occurs when light attempts to pass from a more optically dense medium to less optically dense medium at an angle greater than the critical angle. So these are the conditions. When this occurs, there is no refraction, only reflection. Total internal reflection can be used for practical applications like optical fibers or fiber optics. Now, in order to demonstrate this, we use math. Recall Snell's law, and for the critical angle, n2 equals n1 sine theta critical. Important, all rays with theta 1 greater than theta critical will be totally reflected, because if theta 1 greater than theta 1 critical, then we get from Snell's law that sine the angle will be greater than 1. This is impossible since the sine is bounded between minus 1 and 1. It couldn't be greater than 1. If we examine this figure quickly, for a normally incident ray, it crosses without any deviation. As the angle of incidence increases, the angle of refraction also increases, and it's always greater than theta 1. For the value here for ray 4, it grazes the surface, so we reach the critical angle beyond which the ray will be trapped in the medium. As a summing up, for example, consider two medium, glass and air, glass with an index 1.5, air with an index 1. The first step that you should perform it is finding the critical angle using the formula theta critical equals sine minus 1 of 0.375. So theta critical will be calculated using the calculator. Then if theta 1 increases, theta 2 is larger in case of ray 1 and in case of ray 2. But when theta 1 equals theta critical, theta 2 equals 90 degrees. Finally, if theta 1 greater than theta critical, all light are reflected. All light are reflected and trapped in the glass. Examples of total internal reflection: the reflecting prism. Note that light is going in a transparent medium. Will it cross into air? In fact, no. Using simple geometry, this is a right isosceles triangle, angle 45. This is the angle of incidence, which is 45 degrees greater than the critical angle, so the ray will not cross into air. It will be total internally reflected and goes out from the next side. Other examples of total internal reflection is the formation of mirage. The road seems wet on a hot day. This is called mirage. Why? Since light from the sky will undergo total internal reflection here and looks like a pool of water. Using total internal reflection in our daily life, we can use them in optical fibers or fiber optics, which are used in medicine or in telecommunications. Know that when light is trapped between two media with different indices, light will cross in the medium and will be trapped in it. Now, students, what about dispersion? Dispersion is the separation of light into a spectrum by refraction. The index of refraction is actually a function of wavelength. For longer wavelengths, the index is slightly small. Thus, red light reflects less than violet. The peak is exaggerated. This effect causes white light to split into spectrum of colors. Red light travels the fastest in glass, has smaller index of refraction and bends at least. Violet is slowed down the most, has the largest index and bends the most. In other words, the higher the frequency, the greater the bending. What about the variation of index of refraction with wavelength? The index of refraction depends on the wavelength. In general, it generally decreases with the increase of wavelength. For red color and for blue color here, we can see that theta 2 less than theta 1.